Well, good afternoon, all. I want to start off by thanking Ranjini and Mahesh for this invitation to be here at this excellent workshop. This really been a good program, and I'm really glad to be part of it. Keeping in mind that the audience is almost entirely students and young postdocs, as informed to me by the organizers, I'm sort of keeping my talk in I've sort of organized it in a pedagogical style, okay? So I try to sort of explain various things, even if they should have been in your advanced StatMech courses, etc., as we go along. That's one. And the second is, even if a doubt arises in the middle, please stop me immediately. Okay, don't wait till the end of the talk. Okay. So that's my title. I'm going to talk about the cooperative kinetics of liquid crystals with inclusions. Okay, that's sort of a sort of mouthful, and I'll explain various things as I go along. We're all familiar with liquid crystals, of course. We use them every day, and I'll tell you the kinds of inclusions I'm interested in. In his pre-lunch lecture, Sanath already talked a lot about inclusions in various polymeric systems and so on and so forth. So they're very sort of important at various levels. Okay, so here's an overview of my talk. I'll start off with an introduction, and then I'll move on to my first class of liquid crystals with inclusions, which are ferronematics. So ferronematics are basically an amalgam of liquid crystals and ferromagnetic particles, nanoparticles, magnetic nanoparticles, basically, okay? And I'm going to talk about how you model the system, ferronematics, and then I'll talk about some dynamical phenomena in these systems, which we've given the term slaved coarsening. Perhaps cooperative coarsening would be a better term in these politically correct days, okay? So that's parts B and C. Then parts D and E, I'll move on to a second class of systems, liquid crystals with inclusions. In this case, the system is called living liquid crystals. The inclusions are active particles, and usually the experiments are done with bacteria in these living crystals. Again, I'll sort of tell you about the modeling of living liquid crystals, and then I'll talk about pattern dynamics in living liquid crystals. Let's see how far I get. I'll try to be, I mean, even if I don't cover the entire sort of sequence of things, I'll try to be as clear as I can for the material I discuss, okay? And then I'll end with the customary conclusion, okay? So here's an overview. As I said, an introduction. We're all familiar with liquid crystals. These are intermediate between liquids and solids. They have fluidity in terms of not having translational order, but they have long-range orientational order. Okay, and most of these are organic compounds, and they are used extensively in industry and in our displays and so on and so forth. So here's a cartoon which sort of illustrates the temperature-driven transition of a liquid crystal. You have a bunch of rod-shaped molecules, let's say chalks, a box of chalks, for example. At high temperatures, you have an isotropic liquid with no order of any kind. As you cool the temperature down, a phase transition takes place where on the average, the rods are aligned, okay? That's called a liquid crystal. There's no correlation between the translational degrees of freedom. And then as you cool down further, you can go into a crystalline state. And then you have also translational order, basically, okay? So that's the state I'm going to focus on. Liquid crystals, you can form a nematic phase where the rods are aligned up. They can form, I mean, there's a whole host of phases they form. There are smectic phases where you get rods lined up, and there are also additionally layers. So there's a degree of sort of translational order in that direction. You have cholesteric phases and so on and so forth, okay? I'm going to focus on the simplest of the phases, the nematic phase, okay? I've already said that the order state can have a variety of textures, nematics, smectics, cholesterics, etc. And these are fundamentally important due to their wide applications in displays, okay? So the average orientation in liquid crystals is described by a unit vector n hat, which is known as the director. As I said, this is stuff that most of you would have seen already, but it bears repetition nevertheless, okay? Now let's talk about inclusions or doping. Obviously, inclusions have played a major role in the advancement of modern day industry and technology. Sanath talked about several examples. In particular, inclusion in soft matter like glasses, polymers, and so on and so forth, can be used to improve their mechanical, thermal, rheological properties, etc. Okay, so I'm going to provide a Ginsburg-Landau framework and study the resultant dynamics to study liquid crystals with two classes of inclusions. As I've already told you what the two classes of inclusions are. I'll consider ferronematics first, which are liquid crystals with magnetic nanoparticles. And then I'll consider living liquid crystals, which are liquid crystals with active particles. And as I said, often these active particles are in the form of bacteria, basically. Okay, so these are the two systems I'll consider. And let's then move on to the ferronematics. So now I'm going to consider liquid crystals with a distribution of magnetic nanoparticles in them. And a long time ago, Brochard and de Gennes proposed the inclusion of magnetic particles in liquid crystals and sort of termed this system as a ferronematic, basically. Okay, and the idea was, I mean, why do you want to make these nano inclusions? Well, most liquid crystals have no magnetic response at all. So the idea was to enhance the magnetic response of these systems by including these magnetic nanoparticles. And it's a sort of open up a whole new range of applications and problems, etc. Okay, so that was 1970. Actually, took a long time for Brochard and de Gennes' idea to be realized. The basic problem with including magnetic nanoparticles was that because of the dipole-dipole interactions, these guys sort of aggregate in literally on the time scale of minutes, basically. Okay, so sort of come together, and you can't get a stable functional aggregate of ferronematics. Okay, so the technical problems were overcome in 2013. So that's almost 40 years plus thereafter by the Slovenian group headed by Mertel. And Mertel created the first stable ferronematics using disc-shaped magnetic platelets. Okay, so here's a sort of picture from their paper out there. That's the liquid crystal director, which is labeled as N hat, I already told you. And these are the magnetic nanoparticles. What happens basically is that the liquid crystals form what are called Saturn ring defects, which stabilize the array of magnetic nanoparticles. I don't want to go too much into the details of that, but the bottom line is that you, at the end of the day, you get this aggregate of stable ferronematics with the magnetic moment pointing along the director field on the average, basically. Okay, and then there's a picture of the magnetic response of these. So that's the magnetic field, that's the magnetization, and Mertel and all studied this in various contexts, and then this became a very sort of popular system, basically. Okay, so my idea is to sort of write down we want to write down theories for this system. And what kind of theories do we write? Well, I'm going to work in terms of, yes, please.
So the magnetic moments of is macroscopically ferromagnetically aligned. Is that right?
That's right.
So the system now has a head-tail asymmetry for macroscopic.
It has a, yeah.
There's an interesting thought, which is that there are, as of 4 or 5 years ago, there now exist liquid crystals with macroscopic polar vectorial order.
I see.
I don't know if the symmetry properties of these two systems mean you have the same kind of mechanics or not. I guess the magnetic interactions long range will be different. But there do now exist systems which, even in the absence of magnetism, actually are ferronematics.
I was not aware of that. Okay, thanks. Okay, so as I said, so they were able to generate these ferronematics, and we want to write down models of ferronematics. I should say, by the way, is my collaborator is Varsha Banerjee in IIT Delhi, and a student of hers called Aditya Watts. So that's who I've been working with. Okay, so the starting point of writing down a good model for this system is the liquid crystal order parameter. And again, there's your picture of liquid crystals. That's an average director. There's an up-down symmetry. You don't distinguish between the up and the down direction. So that's just a unit vector. And usually what's called the Landau-de Gennes free energy is written in terms of the order parameter Q. So Q is a rank D by D, it's a rank D tensor, basically, and the Qij is a magnitude, And that's the liquid crystal sort of director, and that's the usual Kronecker delta, basically. Okay, so this again is something I hope many of you have seen before. Just suffice it to say that this order parameter Q is traceless. If you just compute the trace, you'll find it 0. And additionally, it's symmetric. So Qij is equal to Qji. Okay, and this is famous book by the Jens and Prost, where they have all sorts of examples of these free energies that you can write down using this coarse-grained order parameter Q. Okay, so that's what I'm going to use to describe my liquid crystalline field. The quantity S, the magnitude of Q, measures the degree of orientational order about the director n hat. In the isotropic phase, S is 0, and in the nematic phase, S is some large number, 1 in some units, basically. Okay, so I'm going to sort of, for simplicity, stick to 2 dimensions. The formalism works for arbitrary dimensions, but it's just easier to present it in 2D. So in 2D, the Q tensor is just that, and because it's traceless, that is equal to minus that, and because it's symmetric, that is equal to that. So basically, the Q tensor is represented by 2 parameters in 2 dimensions. Very nice. Okay. Next thing we need is a magnetization order parameter, and the magnetization order parameter is just the average magnetic moment of the magnetic nanoparticles. And again, in D equal to 2, that's you have an X component and you have a Y component. Okay, so these 2 quantities are going to be the ingredients of a free energy I write down. And there's an example of a free energy. Let's for the moment forget about the ferronematics part. I'll talk about that later. I just want you to look at this expression for a while. This is a typical Landau free energy, which I believe you would have seen in your statistical mechanics course. The magnetization free energy is this red term out here. And basically, M is a continuous vector. It's a sort of continuous spin. And for alpha greater than 0, you have, well, maybe well, okay, let me sketch this out. Usually you encounter this in the context of a magnet. And in the magnet, you have the free energy plus minus m squared by 2 in dimensionless units plus m4 by 4. And if you sketch this, which I hope all of you have done, the free energy as a function of m is just above. For a plus sign out there, you have a parabolic free energy that's above the critical temperature. And for the minus sign out there, you have this broken symmetry free energy, where you now have 2 minima at non-zero values of the magnetization. So that's for T less than Tc. The reason I've written this down is because one is going to encounter many variants of this in the talk. So it's good to have it on the board. Okay. So that is just the vector version of that Landau free energy. This is the Ginzburg term, which penalizes the variation of the order parameter. Okay, this is something one standardly writes out. The free energy for the tensorial part, for the liquid crystal part, is this expression here. It's again written down on symmetric considerations, and I'm not going to go into the arguments of why you write such a free expression down, but this is the standard Ginzburg-Landau free energy for a liquid crystal. Again, if this coefficient is positive, you are sitting at a disordered equilibrium. The liquid crystal is sort of disordered. And if this coefficient is negative, then you are sitting in an ordered state, basically. That's what you have to keep in mind. Exactly as in this case, if you're sitting above the critical temperature, you're sitting in a disordered state out here. If you're below the critical temperature, you're sitting in one of these ordered states, basically. Okay, so that's the crystalline, the liquid crystal part of the free energy. And then I have a coupling term, and the coupling term I've chosen, though I've written it down in terms of Q and M, is essentially minus n dot m squared. Okay, so what does this term in the free energy do? This term in the free energy makes n align parallel to m. That's one, because if n aligns parallel to m, this term is larger, and this brings the free energy down. And the second thing it does is it's symmetric in n and minus n, in n going to minus n, because you don't want to discriminate between the up and the down states in this simplest version of the theory. Okay, so this coupling term, which is exactly that expression out there, makes the two components N and M align parallel to each other, as was dictated by the experiments of Mertel et al. Basically. And this quantity gamma quantifies the magneto-pneumatic coupling. Okay, so that's the overall free energy that I'm writing down for ferronematics. For those of you who are not that familiar with these kind of formulations, the bottom line is you try to write down the simplest free energy which captures the appropriate symmetries of the system, and then work with that. That was what Landau taught us, basically. Okay, so these coefficients are all various Ginzburg-Landau coefficients. The important ones are capital A out here, which is T minus Tc N. That's the critical temperature of the pneumatic. If T is greater than Tcn, A is positive. If T is less than Tcn, capital A is negative. And the second one is alpha, which is the coefficient of this term out here. That's T minus Tc, the critical temperature of the magnetic component. So if the T is greater than the critical temperature there, that's positive. And if T is less than the critical temperature here, that's negative, basically. And you have this kind of symmetry breaking I've talked about. Okay, so these are the sort of ingredients of our model for ferronematics. I'll use a very similar model later for living liquid crystals. And the next piece of work I do, I'm interested in kinetic effects, dynamical effects. I formulate TDGL equations of the form. That's a typical TDGL equation using this free energy. Okay, so psi is an order parameter. And basically what this TDGL equation is saying is the following. It relaxes the order parameter to its local minima of its free energy. Again, this is something that is sort of textbook material. But the things to keep in mind here are the following. A, if you want to sort of analogy of this equation, you think of a particle moving in a particle moving in a dissipative bath, relaxing to the minimum of its local free energy. I've neglected the inertial term out here. So that's exactly that equation. And the second thing to keep in mind is that one has a non-conserved order parameter here, because both the Q and the M are non-conserved quantities. Okay, at the end of the day, the entire system can have a uniform Q or a uniform M. Okay, there are also conserved order parameters, which I will not get into in this talk. But a good place to read about these formulations is this classic review article by Halperin and Hohenberg. Okay, it's a very old RMP article, but they sort of discuss the role of conservation laws, etc., in some detail. Okay, so I'm going to now write down. Okay. So again, even if you don't follow all the mathematics, that's okay. You can just go home and work it out. My talk will be sort of available online. But basically, that's my free energy as a function of two order parameters, Q and M. And I'm going to write down relaxational kinetics of the model A type using these free energies. And actually, it's very simple doing these functional derivatives. I mean, the equations look a bit ugly, but they're actually fairly straightforward. And usually you use natural scales of the problem to put them in a dimensionless form. And I'm just giving you the expressions in terms of the natural sort of in the dimensionless units. Remember, I'm showing you everything in 2 dimensions. So there's a relaxational equation for, so in 2 dimensions, I had 2 quantities which defined the liquid crystal order parameter, right? So I have a first equation del Q11, del Q12, and then again I have 2 components of the magnetization order parameter. So I have a relaxational equation for that, del M1 by del M2. Again, for the moment, let's forget about the coupling. If you don't have any coupling term, then the relaxational equations for the liquid crystal are just that set of terms, basically. And what that set of terms does is it relaxes you to the local equilibrium. If you have a plus sign out there, the local equilibrium is the ordered phase. If you have a minus sign out there, the local equilibrium is the disordered phase. Okay. Similarly, for M1 and M2, if you don't have a coupling term, that's the sort of primitive system, so to say. And the primitive system, the kinetics relaxes you to the appropriate equilibrium state as time t goes to infinity. Okay. What do the coupling terms do? That's what we want to find out. But I want to sort of emphasize at this point already that the coupling terms are quadratic, okay? So on the linear scale, on the linear level, there are no contributions to the instability from these coupling terms, basically, okay? And that's one. And the second thing I want to say is the following, that of course they both arise from the same coupling term, but I've put different coefficients C1 and C2 in front of them because I've also absorbed things from the order parameter scale, etc. Okay, so later I'm going to consider limits where C1 could be 0, C2 non-zero, and alternatively C1 could be non-zero and C2 zero. That simply depends on whether the coupling affects the liquid crystalline field or the magnetization field. Okay, okay. So I've already said that the minus sign corresponds to a quench temperature above a certain critical temperature, and the plus sign corresponds to a quench temperature below the certain critical temperature. The critical temperature for this guy is naturally TCN, and the critical temperature for this guy is naturally TCM. Okay, so that's the equation I'm going to look at, and that brings me to then part C of my talk. I want to talk about some coarsening problems in the context of ferronematics, and I've entitled that Slave Coarsening in Ferronematics. Okay, so let me again give you the sort of cartoon problem of domain growth or coarsening as it's called. You start off with a magnet at high temperature. It's in a disordered phase at time t equal to 0, and you rapidly quench the temperature below the critical temperature, right? That's your sort of problem 101 of coarsening. So I quench the magnet from above the critical temperature to below the critical temperature at time t equal to 0. That's the phase diagram of the magnet. That's the temperature axis. That's the magnetic field axis. Forget about magnetic field. Just focus on H equal to 0. So at early times, I am, I start off with a system at a high temperature T out there. That's in the disordered or paramagnetic phase. I rapidly quench it at time t equal to 0 to a temperature below the critical temperature and watch the system evolve. At the new temperature of quench, I like to be in either one of two equivalent ordered states, either the up phase or the down phase, basically, right? I've broken symmetry, and now I have two preferred equivalent states. Because I don't have a magnetic field, the states are exactly equivalent. How does the system proceed? This is something that I and many others have looked at for a while. What happens is you develop domains that are rich in the black spins, which is, let's say, the up state, and the white spins, which are the down states. As time goes on, these domains coarsen and coarsen and coarsen. And finally, at time t equal to infinity, one of the phases wins out. Basically, what wins out is random because you're equally happy being up or down. And as I said, the order parameter is non-conserved in this case because you start off with a randomly disordered magnetization, and then you end up with a system which is all magnetized. Okay. So now, this talk is not about coarsening. Well, it's partly about coarsening, but I don't want to go into too many details of it. Let me just sort of tell you that typically the equations that describe coarsening are nonlinear and intractable. Basically, these are sort of standard equations of pattern formation, which are known as reaction diffusion systems. And these are nonlinear intractable. What we've been able to do over the years, we means people who've been interested in these problems, is use the defects between the domain boundaries as an instrument to capture the pattern dynamics. Okay, that's what we've been able to do. So in some approximations called the Gaussian closure approximation, you can actually capture the random walk of these domain boundaries where all the action is happening. And you find out that for simple systems, the characteristic domain size follows a power law. In non-conserved systems like the ordering magnet or the ordering liquid crystal, you get an L raised to power T raised to power half law in time. So that just comes from the interface doing random walks, basically. And this is known as the Lifshitz-Alan-Kahn law. And in systems with conserved kinetics, which arise in what's called spinodal decomposition, which perhaps you've heard about at some point in this course, but this will be the last mention of it in my talk. In systems with conserved kinetics, the motion of the interfaces is slightly more tortuous because you have to conserve the order parameter. You have to conserve the composition of the system. And that leads to getting a slower growth law of the form t raised to power 1/3 with time. Okay. And that cannot be understood on the basis of a simple random walk of interfaces. Okay. That's the key point. Okay, so I want to look at this coarsening problem in the context of ferronematics. So what I've done is, if I go back to my free energy, those are the kinetic equations I'm going to solve. I'm going to start off at high temperatures where everything is disordered. So that means the liquid crystal field is disordered, which is to say that Q11 is 0 plus minus fluctuations everywhere. And the magnetization field is disordered, which is to say that M1 and M2 are 0 plus minus fluctuations everywhere, basically. Okay, so that's my initial condition. And I'm going to let the system evolve. You already know that in the absence of coupling, if I put these C1 and C2 equal to 0, I will evolve to a state dictated by the temperature which I have quenched to. Okay, so now remember, I have two temperatures to play around with. Maybe I should also put this on the board. I'm going to quench to a temperature, and you're going to have to ask the question, where does it sit with respect to the nematic critical temperature? And where does it sit with respect to the magnetization critical temperature, basically? Okay, so if I quench to a temperature below the nematic critical temperature, the system is going to become nematically ordered. If I quench to a temperature below the magnetization critical temperature, the system will become magnetically ordered, right? Those are the sort of primitive systems. And now one wants to ask what the couplings will do, basically. Okay, so let's do this quench experiment and see what happens. So, but maybe I should sort of, well, I've basically just written down what I've put on the board out there. I'm going to study coastings in ferronematics. So I start off with a random disordered initial condition for both liquid crystals and for the magnetic field. There are two relevant critical temperatures. So I can quench to 1, 2, 3, three possibilities. Possibility one is where the temperature is less than TCM but larger than TCN. So physically what that means is the nematic does not intrinsically order, but the magnetization does order intrinsically at this temperature. Okay. Second possibility is that the temperature is greater than that, less than that, which means the magnetization does not intrinsically order, but the liquid crystal does intrinsically order. And then, of course, you can quench to a temperature below both these temperatures, in which case both the components sort of order spontaneously. I'm also going to consider various limits of coupling constants. C1 not equal to 0, you don't have to sort of keep this in mind, but just keep the following picture in mind, that when C1 is not equal to 0 and C2 is equal to 0, if you go back to the equations, the nematic is affected by the coupling, but the magnetization sort of goes on in its own sort of free way, basically. Okay, and then of course you can have the opposite situation where the magnetic field is affected and not the nematic, and then you can have some approximation in the middle. So there's several cases which one can study. I'm just going to focus on one particular case and sort of show you the kind of physics that emerges. The first thing, whenever you're looking at these sort of pattern forming type of equations, is to obtain the fixed points. To obtain the fixed points, you go back to your kinetic equations. What is your state at time t infinity? It's going to be time independent, so this del by del t's will drop out. It's going to be space independent, so these del squared terms will drop out. Okay, so as time t goes to infinity, you'll go into a state which is dictated by the stationary points of this set of coupled equations. And that's what I've written out there. Okay, again, don't worry too much about the precise mathematical details. It's all very straightforward. The equations are a little sort of long. Okay, okay. So now that's the coupled equations which determine the fixed points. And though they look like ugly coupled equations, you can actually solve them exactly exploiting experimental rotational invariance. And I'm going to focus on the case where the temperature is above the nematic critical temperature and below the magnetic critical temperature. And furthermore, C1 is not equal to 0 and C2 is equal to 0. So in the natural evolution, this system would have a disordered liquid crystal and an ordered magnetization field. Okay, so that's the fixed points. You see that the liquid crystal field has also developed an order which is proportional to the coupling strength C1. And of course, the magnetic field was going to be ordered anyway. So that's one possible class of fixed points. And the other possible class of fixed points, as always, is where everything is 0. So everything is in a disordered state. You can do a linear stability analysis about that. Just look at fluctuations and how they grow. And you'll find that the ordered fixed point is the stable state in this particular situation. Okay. So the ordered fixed point, you're starting off with an initial condition in the coarsening problem where all the fields are 0 plus minus fluctuations. And then you relax to this ordered state as time t goes to infinity, basically. That's the pattern dynamics that you're going to expect. Here's a picture of the evolution. The upper field is the nematic field. Remember, the nematic field is intrinsically stable. It intrinsically does not order at this temperature of quench. That's the magnetic field, which it likes to order because I'm below its relevant critical temperature. What happens in this case is that the magnetic field aligns, the magnetic field orders as it is. And in that ordering process also drags the intrinsically stable liquid crystal field into order, basically. That's because M likes to point parallel to N, basically. Okay. So if you look at this evolution, this is the free evolution of the magnetic field. Points where 4 colors meet is a point of a vortex or an anti-vortex. Okay. As in the ferromagnet, the coarsening was driven by random walking interfaces. In this case, the coarsening is driven by random walking vortices. And in other cases, if you have a Heisenberg model or something, you have random walking monopoles and so on and so forth. Okay. And these guys dragged this fellow into a coarsening state. And this is what we refer to as slave coarsening, basically. Okay. Because this intrinsically disordered field is dragged into order by the magnetization field. Okay. One thing I want to emphasize is the following, and I'm just going to do it in the context of the next slide. We get what are called subdomain morphologies. What are subdomain morphologies? Because N is equally happy pointing parallel to M or anti-parallel to M. Well, and N has an up-down symmetry. So basically, what happens is the following: you get these domains of order. The blue stuff is the is sort of the appropriate nematic field, and then you get puncture it with this sort of snapshots of what's called double phase separation. And the snapshots are simply arising because I'm equally happy if N points parallel to M or N points anti-parallel to M. Okay, so that possibility sort of arises in this particular situation. Couple of other things. Growth law saturates for the magnetization field, for the nematic field, but it saturates for the magnetization field because of the formation of these subdomain morphologies. Also, even though the order parameter is continuous, the magnetic order parameter is continuous, the scattering is like function, it gives a Poirot tail analogous to scattering of interfaces, because the subdomain morphologies basically have order parameter pointing up and down adjacent to each other, basically. So lots of interesting sort of kinetics comes out of this particular system, and we've been investigating some of this. We've been sort of trying to argue for the growth laws, etc., and have sort of learned a few things about the system. Okay, I can take a 5-minute break before I sort of go into the next set of things. Yes, please. Yeah. Yeah, maybe I rushed through this bit. What you should do is the following. You start off with a disordered field at t equal to 0. Okay. So that would mean you had an infinite density of blue and green structures. As time goes on, you order into one quadrant or in the other quadrant. Because there's an up-down symmetry, the angle can only be 0 to pi. And as time goes on, the domains become larger and larger. And finally, at the end of the day, at infinity, you've broken symmetry and everything points in one direction. Okay, that's the picture. But sorry, what's your question? No, well, the system is at the same temperature, but T, which I quenched to, is above the critical temperature of the nematic field. So this nematic field is showing coarsening, even though it is intrinsically not desirous of doing so. And T is less than the critical temperature of the magnetization, in which case you expect that to show coarsening, and sure enough, it's showing coarsening. So the slave coarsening is that this field is dragging this field. It's dragging it also, and that's the second thing I should have emphasized, which I did. If you go back to the kinetic equations, because these are quadratic terms, it's not dragging it through a linear instability. It's dragging it through a non-linear instability. Okay, if you just sort of do the linear stability analysis, you find that, which is to say that this guy has to grow for a while before it finally affects the other field and drags it into instability. Okay.
Can you just show the equations again?
Sorry.
Oh.
Yeah. Okay. You should come next. Yeah. Yeah. The kinetic equations. Yeah. So that's the intrinsic part for the Landau-Digens free energy.
Yeah.
That's the intrinsic part for the XY free energy. And these are the coupling terms, basically.
Right. So you're saying that
quadratic. So if you do stability analysis, M1 equal to 0 plus minus fluctuations, all of these terms drop out in the stability.
Right. So it's not as though you can solve for M and I mean, you can solve
and find the instability points.
It's not a linear instability at all, but I see. Okay, thanks.
But it shows up in the fixed points when you calculate them. In the fixed points, you get non-zero values for this value, which are obviously proportional to the coupling strength C1. Because the coupling is why these guys are ordering in the first place. Yes, you had a question there? I'm just showing it for a 2D system for simplicity. Exactly the same formulation works for a 3D system. The growth laws would be the same, as a matter of fact, because these non-conserved order parameters are very dull in that they always give this diffusive power law growth. At most, you can have a logarithmic correction in some cases. Okay. Invariably, it's square root of t. That's a good sort of way of looking at it. Yeah. 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 Then you would have a linear instability, but that would require a polar liquid crystal also. Yeah. I don't think so, because then you would have a linear instability in that system, because these terms would become, I mean, we did think about that, then you actually have a linear instability. And I think the physics will be quite different. Okay. Okay. Any other questions? Yeah, please. How sharp are they? Well, actually, they are not domain boundaries as such. What's happening, see, I'm plotting an angle field for the nematic out here. Okay, maybe I should have spent a little more time on these pictures. So where the angle lies between 0 and pi by 2, it's blue. Where it lies between pi by 2 and pi, it's green. Where it lies in this quadrant, it's blue again, because there's an up-down symmetry. And if it lies in this quadrant, it's green again, because there's an up-down symmetry. Okay, so you don't have domain walls in this case. What you have are junction points of two colors, which correspond to what are called half defects. Because see, in the magnetic field, you have a vortex or an anti-vortex. The counterpart in the liquid crystal is a half defect plus half defect or a minus half defect. Okay. And whenever you're ordering with a vector order parameter, you always have, because of the continuity of the order parameter, you have the possibility of these defects. So you don't have domain boundaries in this case. Okay, but you can think of the size of the defect as a typical length scale in the system, basically. Does that answer your question? Huh? Okay, good. Any other questions? Okay, if not, then let's move on to sort of part 2 of my talk. I have about 20 minutes, but hopefully that should be enough to give you a flavor of this second class of liquid crystals with inclusions. And these are what we call, well, not what we call, what the experimentalists have called living liquid crystals. So I'm going to talk about the modeling of living liquid crystals. And of course, active matter has been popularized hugely, particularly in India by my friend Sriram, who's one of the leaders in this field. So we all know what active matter is. You must have heard talks on that also. An assembly of self-propelled mechanisms, organisms is termed as active matter. These systems continuously dissipate energy. And I think one of the really good papers to read about it is now sort of a classic in the field, is this review article by Marchetti, Giovanni, Ramaswamy, and others, basically. Okay. Obviously, there are many examples of active matter in biology: bacterial colonies, bird flocks, shoals, animal herds, etc. Yeah, of course, it's there's a picture of a shoal of fish, and there's a picture of a bird flock. And then you can have also synthetic examples of active matter, like photoactivated colloidal particles, vibrated granular matter, which I think Sriram and his collaborators were the first ones to talk about, artificial swimmers, Janus particles, etc. Okay, and again, just to sort of convey to you the flavor of the beauty of the physics that's involved, what's fun in these systems, as in all statistical physics systems, is how objects with nearest neighbor or next nearest neighbor interactions can develop long-range order. Okay, that's what happens in the Ising model, that's what happens in the liquid crystal, and that's also what happens in these flocks of birds and fishes and so on and so forth. Okay, so the now particular experiments I focus in on are an amalgam of liquid crystals and bacterial active matter, and this system has been termed as living liquid crystals. And it started to get talked about 10 years ago, basically. Okay, and at that time there was no, I'm not a very good theory for this system, not much of a theory at all, actually. Okay, so the interaction between the active particles and the medium provide a rich variety of dynamical patterns, again suggesting lots of applications. Let me talk about the applications as we go on. Okay, so here's an experiment with this form of bacteria in liquid crystals, and the bacteria of about micrometers, the diameter is that, and the typical liquid crystal molecules are a few nanometer in length. Okay, so what these experiments of Zhu and Peng and others did basically is they pre-tailored liquid crystal, they printed liquid crystal circuits, so to say, on a substrate, and then asked what the active bacteria do. How do you print a liquid crystals on a circuit, on a substrate? Well, you could do it with boundary conditions. You could set the right boundary conditions and you could get a designated sort of configuration. So in this case, the designated configuration is what I was mentioning earlier. There's a plus half defect there and a minus half defect out there. And then that's the rest of the system, basically. Okay, it's like having a vortex, heavy vortex, and a semi-anti-vortex. Okay, what do the bacteria do? Well, the bacteria, that's the picture of the bacteria, I think. At the end of the day, what the bacteria do is they move from the minus half defect, which is this guy, to the plus half defect, which is this guy. Okay, so that was the experiment of Peng et al. I think Genkin and all went into this in more detail and sort of identified why exactly this migration takes place from the minus half defect to the plus half defect. Again, in this case, the experimental sort of story lies on the fact that the bacteria point parallel to the liquid crystal locally. The liquid crystal is apolar, so again, it has an up-down symmetry, basically. Okay, what is this thing about microfluidics? Well, again, it's the same story. You can sort of etch a liquid crystalline sort of configuration onto a plate, and then you can make these bacteria sort of swim perpetually around the vortex at the center of the plate. Okay, so you can, I guess, you can sort of dictate the motion of active matter by providing the right liquid crystalline configuration. You could also move in the other direction, but these guys were more interested in guiding bacteria rather than guiding liquid crystal dynamics. Okay, so it's possible to have command over active matter, and that opens up various possibilities for microfluidics and so on and so forth. Okay, one wants to now write down Ginsburg-Landau models for this. I'm going to sort of follow the same strategy I did for the previous problem. I'm going to work in terms of coarse-grained free energies. The important thing is to identify order parameters. Remember that the coarse-grained free energy for the liquid crystal I've already written down. The coarse-grained free energy for the liquid crystal, if I can get back there, is basically that term, this term up here. This is the local, what's called the Landau free energy, and this is the Ginsburg penalty term, which penalizes gradients in the system. Okay, the rest of it obviously does not exist from living liquid crystals. We have to identify what living liquid crystals will add to this free energy. Okay, so living liquid crystals are usually modeled in terms of two order parameters. One is the polarization vector of these bacteria which are moving, and the second is the density. And this is neat formulation. The standard equations are these Stoner 2 equations at the coarse-grained level. And there's this neat formulation in Sriram's RMP article in terms of this free energy. Notice this looks very much like our 5/4 free energy. It has some more terms, of course, which play a fundamental role. But the first few terms are reminiscent of our 5/4 free energy. And the Stoner 2 kinetic equations are basically a continuity equation for the rho field, the density field, and a relaxational equation for the velocity vector field. Okay, this is like a TDGL equation, except it has this additional term out here, basically. Okay, the free energy we propose for living liquid crystals is the following. I have the free energy of active matter, which is this expression. I have the free energy of the liquid crystal, which is that expression I had written down earlier. And I then put in a coupling term. And again, I put in the same simple coupling term, n dot p the whole squared. Okay, what does n dot p the whole squared do? It makes the bacteria want to point parallel to the local order parameter of the liquid crystal, dictated by the experiments. Additionally, there's an n going to minus n symmetry. If you didn't have an n going to minus n symmetry, then you would not need the square term out here, basically. Yeah. So the liquid crystal molecules are a few nanometers in length. Their scale is about 50 micrometers, I guess. The distance between the defects is about 20 to 25 micrometers. Okay. But at the microscopic level, yeah, well, no, they're still very different in size. Yeah, I guess. Okay. Okay. So that's my free energy for living liquid crystals. It's this active matter bit, which is that. The liquid crystal bit, the Landau-de Gennes free energy, which I had written down earlier. And this coupling term, which is again the same old coupling term I had used for my ferronematic system. Okay. So again, I plug these into the equations, go into dimensionless variables. I don't want to sort of go into all those details out here. But basically, you have, again, I'm writing it down in 2 dimensions. You have coupled equations for the following 5 quantities. Q11 and Q12 define the liquid crystal. P1 and P2 define the velocity field of the active matter. So it's dry active matter. There's no other additional fluid in it. And rho defines the density of active matter. As I understand it, in active matter, this quantity plays the role of my plus minus 1 coefficient. Okay, so the active matter spontaneously orders if rho is above, the average density is above a critical density, and this active matter intrinsically does not order if rho is below that certain critical density. Okay, so that plays the role of critical temperature in the system. Okay, we've looked at pattern formation in these systems. Again, this is something which just came out a few weeks ago. You can have various cases. Obviously, when the liquid crystal could be unstable, the active matter could be stable to fluctuations and so on and so forth. I don't want to go into the details of that, but again, you can exploit rotational invariants to find the fixed points. You can do the linear stability analysis. You get all these sort of long-looking expressions. But basically, the point I want to emphasize, I can go into details if somebody wants to know them. The point I want to emphasize is that you can get the entire phase diagram of the composite living liquid crystal. Okay, so I'm going to consider a case where T is greater than Tc. That means the nematic does not like to order. Okay, and rho is greater than rho c. The active matter likes to order. Okay, that's the two limits I'm going to consider. And obviously, remembering our discussion about slave things, one might expect this guy to drag this one into order. Okay, and that's actually what we find happens. So here's a phase diagram of the system obtained from this linear stability analysis. C0 is the coupling strength of the liquid crystal and the nematic. And for C0 equal to 0, you just have the pure adulterated systems. Let's first discuss what happens on that axis. For rho 0 less than rho c, this guy is negative. So that's there. The liquid crystal does not order. The active matter does not order. As you crank up rho 0 just above rho c, small values out here, you find a banded state, which people have paid a lot of attention to in the active matter literature. And then finally, as you crank it up past this critical value, which you can get analytically, you find that you get a homogeneous ordered state in that case. Okay, and then as you turn on the coupling, you find that this region of the banded state grows larger, as a matter of fact. And if you're moving in this direction, it's like a re-entrant phase transition or something, basically. Okay, so you can go out further in rho 0 minus rho c and still get a banded state. And then, of course, if you go to large enough rho 0 minus rho c, you have an ordered state. Okay, so here's a schematic of evolution from a random initial condition. Again, it's a coarsening type problem, except the system doesn't go to a fixed point. I mean, it goes to a permanently moving steady state. The first field I'm plotting out here is for the active matter. I start off with a random initial condition for rho, the density field, which is above the critical density, and P, the polarization field, which is the velocity field of the bacteria. As time goes on, some kind of dynamics emerges, and finally it settles into a steady state where a band of dense material, that's the dense material out there, moves in this direction in a sort of background of rarer material, of dilute material, so to say. Okay, this band basically just keeps moving around, and that's the steady state of the system. The liquid crystal, which was not prone to order because I have a temperature above the critical temperature, also reflects this, as a matter of fact. And the reflection is simply that, again, you start off with a random initial condition. I'm plotting a color scale of the order parameter. Again, it looks random, but you can obviously see that there's the same patterns, basically. And finally, you develop a band of order in the liquid crystal, which rotates around at the same velocity as the band in the active matter. And I mean, if you think of it in this language, in this region, the liquid crystal is ordered. In this region and this region, the liquid crystal is disordered. So you have the coexistence of order and disorder. And nonlinear people have called this a chimera state. So that's a nice sort of term for it, a chimera state. Okay. Of course, this is also a chimera state in the active matter. Okay. We've done some further experiments, but I'm running out of time. Let me just sort of quickly tell you what happens for another random initial condition. I start off with a random initial condition. So here I'm plotting the active matter fields. I start off with random initial condition. Here I develop, after some evolution, lumps of dense material. I develop 3 lumps of dense material, and that's the velocity field, the arrows. The dense material is moving in that direction. It undergoes a rather nonlinear and complex collision with these 2 lumps. That's a collision, and then finally comes out unscathed. So this is what we term as an example of a 2-dimensional soliton. Okay, soliton is an object that survives complicated nonlinear collisions with other solitary waves and then comes out unscathed. Okay, so this is an example of a soliton, and the sort of interesting thing is that it's in 2 dimension. In the well-known soliton equations in the physics literature, they're mostly one-dimensional, spatial dimensional equations. Okay, so this is a soliton. It's a localized lump which has integrity under collision in 2 dimensions also. Okay. Okay, so that brings me to my conclusion and maybe a last set of questions. So we've studied 2 examples of liquid crystals with inclusions. Ferronematics, which is a system proposed by Brochard and de Gennes, and living liquid crystals, which is a composite of liquid crystal and bacteria. Okay, and then it's reasonably clear how to write down a time-dependent Ginzburg-Landau model of these systems. We actually study these time-dependent Ginzburg-Landau models. But before that, let me say that in the sort of presentation today, I have used a simple model where the inclusion particles, the magnetic particles or the bacteria, point parallel to the nematic liquid crystal. Okay, but actually it's very straightforward to modify the free energy so that they point at random angles. I mean, experimentally that's possible, that they don't point, they can point perpendicular to each other and so on and so forth. Okay. We studied the phase diagram and kinetics of these models, and sort of the take-home message is that the ordered component can drag a disordered component into order. Okay, a kind of slaved ordering or a cooperative ordering, and this can be exploited perhaps for various sort of uses subsequently. Okay, thank you.
I was hoping for the younger members of the audience, not returning students, to ask questions first. But no, I was actually wondering about 2 things. One is, if I remember right, in the bacteria plus liquid crystals paper by these guys, by Zhang, those guys, one of the dynamical interactions they had was that the bacterium tries to align with the local nematic axis, but not to the same degree as the local nematic axis tries to respond to the bacteria. Right. So a non-reciprocal interaction that can't be written in the form of your QIJ, PIJ.
The energy form, that's right.
So you haven't looked at the effect of that in the course.
We've not looked at that.
So that's going to give you lots of pursuit and escape states and so forth.
I guess, yeah.
So you actually haven't looked at that on coarsening, for example.
We haven't looked at the limit yet. In our ferronematics, I don't know whether this C1 not equal to C2 case can be realized.
No, it can't be. I mean, if it comes from energy function,
free energy, it can't be realized.
Yeah. So you can't. Yeah. But the other question I had is, these solitons that you have,
right,
do they correspond to anything that, is there a reduced PDO differential equation that corresponds to something that's already known? You know, does it correspond to some classic soliton?
No, because as I said, most of the classic solitons are one-dimensional systems.
Right.
You could have a trivial translation of a one-dimensional system with a 2D soliton.
Yeah.
But these lumps, localized lumps, there's not very many examples of 2D completely integrable systems.
So this is a new soliton.
Well, no. I won't stick my neck out that far, because the classical solitons are usually in the context of completely integrable Hamiltonian systems. These are not completely integrable Hamiltonian systems. These are dissipative systems, but it does everything that you expect a soliton to do. So maybe it has some structure in a reduced language where it is akin to a Hamiltonian system.
Because I know that in
You can usually write dissipative systems. If you raise the dimensionality or something, you can write them as in a Hamiltonian formulation or something.
No, because in the just the flocking model by itself,
Yeah.
people have studied soliton-like solutions in some reduced description.
Right.
Already.
Owner and two have actually.
No, these guys, Tyer and company had looked
I
at
see.
some of this stuff.
But was it in 1 dimensions or in 2 dimensions?
Effective one-dimensional.
The toner 2 thing was in 1 dimensions, I remember. Yeah. Yeah. But yeah, no, that's something that I want to play around with a little bit and see whether there's a Hamiltonian formulation of this. If there's not a Hamiltonian formulation, you don't have, see, the key thing about 1D solitons is that you have all these conserved quantities. You have an infinity of conserved quantities and then action angle variables. It's a very beautiful mathematical framework. Yeah, I'd like to see how much of that might apply. Well, go ahead.
Okay. So you said these are dry systems.
Yeah, in the sense that the velocity field is only from the bacteria. There's no velocity field from a liquid medium they are immersed in.
Okay. If I could think how this living matter, then how they are moving in a dry system? How?
Well, I mean, an ant moves, right? In a dry system, it moves on the ground, huh?
Okay.
I mean, the motion has nothing to do with whether they're in a liquid or not. Being in a liquid, immersed in a liquid, gives you a whole lot of new physics and nice physics, but
Hydrodynamics and those are the things will appear.
sorry?
Hydrodynamics and those things will appear if you have a liquid.
Yeah, yeah. So this is, yeah, as I said, ants locomote. I mean,
Okay.
bacteria locomote in dry.
I heard of things they call nematicons.
Nematicons.
Solitons in a nematic fluid.
I'm not familiar with this concept. Yeah.
Yeah.
What? Yeah. What
I just wanted to float that name, nematicons.
sounds like Comic Con, but not connected, right?
So,